When you look at a massive skyscraper or a super intricate piece of machinery, have you ever stopped to wonder what's really holding it all together? So often, it's a weld, just a tiny seam where metal is fused. But the real secret to its incredible strength, well, it's not something you can see. It's all happening at a scale that's almost impossible to imagine. Okay, let's dive into this hidden world together. So, to get started, I've got a question for you. What on earth could a giant skyscraper have in common with a tiny little grain of salt? I know, it sounds like a riddle, right? But the answer is actually the key to understanding, well, pretty much everything about how we build our modern world. It all comes down to what they're made of, deep, deep inside. Believe it or not, the answer is crystals. Yep. On the inside, at a microscopic level, they're both just a collection of tiny, organized crystals. And this is especially true for all the metals that we rely on every single day. Now, in metallurgy, we call these little microscopic crystals metal grains. And honestly, the best way to picture them is to think of Lego bricks. Every single piece of metal is built from countless of these tiny interlocking grains. The size, the shape, how they all fit together, that arrangement determines almost everything about that metal's strength and properties. All right, so let's zoom in, way, way in. We're going to leave the world we can see behind and travel down into this secret world inside the weld itself. Because this is it. This microscopic battlefield is where a weld's strength is either forged or completely broken. So what are we looking at? On the one hand, you've got a weak weld. See those large, kind of clunky, irregular grains? Think about building a wall with a bunch of mismatched, crumbling bricks. It's just not going to be strong, right? It's going to be super prone to cracking. But on the other hand, a strong weld has these beautiful, fine, uniform, tightly packed grains. That is a solid, reliable structure that can resist all kinds of punishment. So here's the key takeaway. Smaller, more uniform grains mean a stronger weld. It's that simple, and it's absolutely critical. But here's the thing. Getting those perfect tiny grains isn't some gentle, delicate process. Oh no. Welding isn't like gluing metal together. It's a trial by fire and force. It's a violent, chaotic event that completely scrambles and transforms the metal's internal structure. Just think about what's actually happening here. First, you're hitting it with intense heat, melting or at least softening the metal. Then comes the really crazy part, severe deformation. The metal is literally being stirred or pressed or fused together. And finally, it cools down fast, freezing that brand new structure in place. Every single one of those steps is a massive shock to the system for those tiny grains. So this brings us to the million-dollar question, right? If the whole process is so incredibly chaotic, how in the world do engineers control it? How do they steer this violent transformation to create those perfect, fine, strong grains instead of just a weak, brittle mess? Well, the answer is pretty amazing. It all lies in the science of control. Over decades of research, engineers have learned not just to manage this chaos, but to actually harness it. They figured out how to tame these tiny little crystals. And the hero of this whole story has a pretty cool name, dynamic recrystallization. You can just call it DRX. The best way to think about it is like a reboot for the metal. That intense heat and force we talked about, it actually destroys the old, large, weak grains. And then, in their place, it forges brand new, tiny, and incredibly strong ones. It's literally a process of controlled destruction and rebirth, all happening in a split second. So how do they actually control this reboot process? Well, today's engineers have a whole toolkit of advanced techniques, and they're all designed specifically to master dynamic recrystallization. Let's take a look at a few of these awesome tools. First up, we've got something called friction stir welding, or FSW. Now, instead of melting the metal, a special rotating tool is plunged into the joint. It generates this intense heat from friction and literally stirs the two pieces of metal together like a really thick dough. This gives engineers an unbelievable amount of control over the heat and the deformation, which, of course, means they get amazing control over the final grain structure. And the results? They're pretty stunning. A 2025 study by Kim and his team working on stainless steel found that FSW could slash the average grain size by over 22%. That is a massive reduction at the microscopic level. So what did that 22% drop in grain size actually do? Well, it led directly to a 4.29% increase in the weld's hardness compared to the original metal it came from. Now, I know, 4% might not sound like a lot, but trust me, in the world of material science, that is a huge leap. That's the kind of improvement that lets us build lighter, stronger parts for everything from spacecraft to surgical tools. It's proof positive. Smaller grains mean stronger material. And this isn't a one-trick pony either. It works across all kinds of different materials. Just look at these studies on joining dissimilar metals, which is famously difficult to do. In 2024, Mao's team got a super strong bond between aluminum and copper. A year before that, Sundar's team hit an incredible 289 megapascals, joining aluminum and titanium. These aren't just numbers on a chart, they represent strong, reliable joints where they used to be nearly impossible, all thanks to controlling those tiny little grains. Okay, so what if you took that awesome friction stir welding and gave it another superpower? That's exactly what Pulse Current Assisted FSW does. By sending tiny electrical pulses through the material while it's being stirred, engineers can refine that grain structure with even more mind-boggling precision. It's another layer of control. So just how much better can it get? Well, a 2024 study by Fahad and his colleagues used this exact technique on magnesium alloys. And the result? A tensile strength of over 314 megapascals. That is a massive level of performance unlocked just by adding a targeted electrical pulse to the mix. Incredible. And for our final tool, we're really jumping to the cutting edge. We're talking about combining 3D printing with welding. This lets engineers build parts layer by tiny layer, which means they can essentially design the microstructure, the grain structure, from the ground up. They can even add nanoparticles to help guide the whole process. A 2023 study from Zhong's team shows just how insane the potential is here. By adding tiny titanium carbide nanoparticles into an aluminum alloy during the process, they crush the grain size from over 111 micrometers all the way down to just 12.5. And the strength? A colossal 355 megapascals. This isn't just engineering, it's practically building materials atom by atom. Okay, so let's zoom back out. We've been deep in the microscopic world, but all of this incredible science has huge implications for the big, macroscopic world that we all live in. This is all about building a stronger, safer, and way more efficient future. So what are the big things to remember from all this? First, a weld's true strength is hidden in its tiny grains. Second, welding isn't gentle, it's a process of controlled chaos. Third, the goal is always the same: create the smallest, most uniform grains you possibly can. And finally, modern science is giving us some absolutely incredible tools to make that happen. And hey, this isn't just my opinion. As the researchers in this field put it, mastering these factors lets us tailor the internal structure of a weld. We can literally design it to get the absolute best performance possible, whether we're building a spaceship, a bridge, or a tiny medical implant. And that really leaves us with a fascinating final thought. We've only just scratched the surface of what's possible here. As our ability to see and to control this hidden microscopic world gets better and better, what kind of future can we build? What amazing new materials and technologies are just waiting for us to unlock them?